Welcome to this explainer. Today, we're doing something super exciting. We're going to break large language models right out of their isolated little boxes. We're moving way past the theory and actually looking under the hood of modern AI systems by building a tool registry entirely from scratch. We'll explore the architectural magic that lets an LLM stop just predicting the next word and start actually doing things in the real world. Let's dive in.
Here's a quick look at our roadmap. We'll cover breaking LLMs out of boxes, the power of abstraction, building the base interface, coding the tool registry, execution and security, and finally, the future of AI agents.
Let's kick things off with Section 1, breaking LLMs out of boxes and connecting them to the real world. To really get why this matters, we first have to understand a fundamental limitation of these models. Without tools, an LLM is basically just an isolated reasoning engine. Sure, it has vast knowledge up to its training cutoff, but it's completely trapped inside its neural network. It can't check today's weather, it can't run complex math reliably, and there's no way it's updating a database. But the moment you introduce tools, well, the paradigm shifts entirely. The LLM essentially becomes an intelligent operating system. Think of tools as the digital hands that allow the model to execute actual real-world actions, retrieve live data, and automate tasks. It's a total game changer. Moving right along to Section 2, the power of abstraction and separating logic from services. So to actually give our LLMs these digital hands, we need what's called an abstraction layer. Basically, this is a component that hides all the messy underlying implementation complexity from the language model itself. It acts like a universal translator. Look, the LLM really shouldn't have to care if the tool it wants to use is powered by a REST API, a massive SQL database query, or just a simple local Python function. The abstraction layer handles all that messy reality, so the LLM can just focus on what it does best: reasoning. Abstraction is absolutely crucial because it completely separates complex communication logic from the LLM's thought process. Without it, you're literally forcing the LLM to memorize exact API endpoints, authentication headers, and network protocols. It's like asking it to write a raw HTTP request from scratch every single time. But with an abstraction layer, the LLM only sees a clean, perfectly standardized command, something simple like calling a weather tool and just passing in the city name. This makes the whole system so much easier to maintain, incredibly portable, and vastly reduces the chances of the LLM making a silly syntax error. Okay, Section 3, building the base interface. This is where we lay down the foundation. With that vital theory out of the way, let's jump directly into the code and actually start building our framework. We're going to follow these 5 sequential steps to construct a simple, highly practical tool system. We'll start by defining the rules, then build a specific tool, catalog it, create an engine to run it, and finally, test the execution. All right, step 1 is standardizing our tool API. Think of your base interface kind of like the core shape of a puzzle piece. In your code, you define a base tool class. Every single tool you build from here on out absolutely must inherit from this class. This ensures it fits perfectly into your system. It forces every tool to have a specific name attribute and an execute method. If it doesn't fit the puzzle, the system just throws a not implemented error. It's a strict bouncer for your code. For step 2, we take that base interface and extend it to create a specific tool, in this case, a calculator. Just like plugging in a new appliance into a standard wall socket, inheriting from the base tool class ensures our calculator safely connects to the broader system. In Python, you just override that execute method with your specific math logic, and boom, the system instantly knows exactly how to route power to it. That brings us to Section 4, coding the tool registry, which is essentially our centralized catalog. So now that we have a customized calculator tool, we need a reliable way to manage it within our system so the LLM can actually, find it. Enter the tool registry. Think of this as a centralized catalog and plugin manager. It stores all available tools, tracks their versions, and exposes their capabilities so the LLM knows what's on the menu. Without a registry, the LLM simply cannot discover tools on its own. You'd end up with a tangled, hard-coded mess, constant tool conflicts, and absolutely zero scalability. The registry is basically the brain's index of available skills. For step 3, we actually build this catalog. And honestly, in code, this is often just a simple dictionary mapping. Think of it like a ledger. We map the string name calculator directly to the executable calculator tool class we just built. It's that simple. If we want to add a weather tool tomorrow, we just pop a new entry into this ledger. Alongside the registry itself, we define the tool metadata. This acts as the instruction manual for the LLM. The absolute most vital part here is the input schema. It uses JSON schema validation to clearly tell the LLM, hey, if you want to use the calculator, you have to provide an input called expression, and it has to be formatted as a string. This allows for intelligent tool selection and guarantees that the data coming from the LLM is properly structured before we ever try to run it. No garbage in, no garbage out. Let's move on to Section 5, Execution and Security, because running code safely is kind of a big deal. Next up, Steps 4 and 5. This is really the climax of our system, the execution engine. When we instantiate our tool executor, it acts as the main gears of our system. It takes the validated request, routes the input data, like the string 5 times 10, into the calculator, grinds through that standardized execute method we set up earlier, and outputs our final result. But we have to talk about the execution logic itself. In Python, evaluating a math string often uses the built-in eval function. But as we all know, things can break. You absolutely must wrap this in a try-except block. Think of this block as a safety net. If the LLM somehow drops a malformed equation into the system like a heavy rock, the accept net gracefully catches the error. That prevents your entire application from crashing and burning. I really need to pause here for a second, though. Evaluating dynamic code, like a string, using eval, introduces massive security risks. I'm talking about things like prompt injection, where a malicious user tricks the LLM into executing dangerous code, or arbitrary code execution. These are real, serious dangers. Because of this, sandboxing your environment and implementing strict permission controls are absolutely non-negotiable best practices. You have to validate inputs against your schemas, filter outputs to prevent data leaks, and definitely set API quotas to prevent abuse. Finally, we arrive at Section 6, the future of AI agents and how we scale all this up. Real-world, production-grade enterprise architectures take the simple Python foundation we just built and absolutely supercharge it. To scale up, these big systems add powerful features like asynchronous execution, so the system doesn't just freeze up while waiting for an API response. They use streaming for real-time user feedback, tool caching to save money on repetitive queries, and parallel tool calls. That means the LLM can literally search the web and query a massive database at the exact same time. And the coolest part? Major industry frameworks implement the exact same registry and abstraction principles we've covered today. Whether you're looking at OpenAI's function calling, LangChain's tool wrappers, AutoGen, or the new Model Context Protocol, or MCP, which standardizes tool communication, they all rely on these core concepts: interfaces, metadata, and registries. That's the secret sauce, connecting reasoning engines to real-world capabilities. We've seen just how powerful a structured tool registry can be today. But as we look toward a future of self-healing tool pipelines and highly dynamic workflow orchestration, I want to leave you with this final provocative thought. What happens when AI systems begin autonomously discovering, generating, and orchestrating their own tools in real time? The architecture we built in this explainer today is really just the beginning. I hope this helped demystify how AI actually interacts with the world. Until next time, keep exploring.